All right, welcome everybody. We are starting at 10:30, start on the dot. We got a lot of information to cover today. If you guys haven't met me or don't know who I am, my name is Randy Plumley. Will be your presenter today. I'm the Energy Codes Program Manager for SPEAR. So I do Energy Codes training, webinars, as well as in person. So we've got a few things that's changed up about some housekeeping stuff, but just to get started, this webinar is being recorded. It will be available afterwards, usually within about 72 hours. It should be uploaded on our YouTube channel. You can find that by going to our website at eepartnership.org, or you can search SPEAR, SPEER, on YouTube directly. We've got probably over 150 or more from a wide range of energy codes, HVAC topics, CELC that Sean does are on there. Our 5 and 5s are on there as well. You can check those out. As always, today's session is eligible for the ICC CEUs. This is what we're going to change up a little bit. But to receive credit, you must be present for at least 75% of the presentation. If you're using someone else's email address or you're in a group that's logged in, please email Kathy back with the survey stating that who was all in the room and attending under one login. So within about 72 hours, you will, as normal, receive the email from Kathy Lawrence for the brief course evaluation survey. Please complete that and return the survey. And then you normally would get, and I think we're going to do it this time, you will get your course completion certificate. However, when you do send that survey back, we are going to change some things up. We're testing out another way to do it. Other companies are doing this as well. We're going to report it directly to ICC. So in addition to what you normally do, here's what we're going to do basically is when you send that survey back, it's very important that you use your email address that you access your ICC account with. So if you have your personal for ICC, but you're using your company to register and log in for the webinars, be sure and use whichever one is associated to your ICC account. Once you do that and complete the survey and you send it back, Kathy will upload a roster directly to ICC. This will immediately update your account showing that your CEUs have been awarded. You'll also receive an email stating that as well. So if successful, if you use the correct email address and it's associated with your account, you'll no longer have to report these to ICC. You won't have to download the certificate. You won't have to keep up with all of that. I know a lot of you guys wait till your 3 years are up and then you try to send it in. This will update it automatically. So in case you forget about this one, you don't have to try to hit us up for trying to get a certificate. You guys will already have it in your account. As always, if you have any questions, email me, email Kathy, ask. On this first one, I'll repeat again that we're just going to probably do it both ways. But going forward after that, if all this was successful, the way we'll be doing this is just reporting directly to ICC. As always, the chat feature will be open. I have it up right now. The Q&A feature is open as well. I have that open up as well. You guys feel free to put anything in there you would like to discuss, talk about, or have a question on, and then we'll either go through it when the questions arise or we can wait till the end, depending on if it's about that slide that we're on. So if you're new to SPEAR and you haven't joined us before, we are one of 6 regional energy efficiency organizations. We cover Texas and Oklahoma. We offer training, webinars, in-person sessions, as well as field support. We have a lot of case studies on our website. We also do some other in-person stuff in and around Austin. We work with local municipalities to help adopt energy codes as well as amendments to energy codes. I sit on the meetings, the committee meetings for North Central Texas COG. We actually go through the amendments so every time a new code is out. So I assist cities around Texas and Oklahoma to actually have them reach out to us and be able to either present training to them personally and in person and or help them with field questions that they have in the field. So if you have any questions with Energy Code, ASHRAE 90.1 on any version of the code, if you're a plan reviewer, building official, a third party, I'm always happy to help. Just reach out to me and we can go from there. If I don't know the answer, as always, I'll find somebody that does and we can get you an answer to that. So let's get started with all of this. So C403 section of the 2024, there's quite a few changes in here. I've got a lot of information on every slide, so you guys will probably want to have mark this video in the future and you can go back and rewatch it. I can send the slides out with the notes that are on here as well if you want to use that for training in your office as well. So Section C403.1 sets the foundation for all mechanical system compliance paths under the 2024. So it tells us what systems must comply and which option designers and reviewers can choose. As I go through all of this, most of what I will do on these slides at the end will be tips for plan reviewers and tips for field inspectors. So if you guys have pen and paper, be sure and take some notes with that. If not, you can go back and rewatch this. So this is essentially the gateway to all the mechanical system provisions. It defines what systems are covered and then outlines the compliance routes available. So expanded compliance option in the 2024, we have a compliance option for building mechanicals that have been expanded to include section C409. We won't get too deep into that here during this webinar. We'll do that in a future webinar, which is a newer section offering additional compliance path. Some say this may be easier for compliance. Others say it's just changing it up again and it may be more difficult to learn it. But I think once you figure it out, it'll probably be a friend of yours to do some design and development for commercial. So designers now have more flexibility depending on the system type and building use. It's all based on that. But on the compliance side of that, we're looking at option 1. This is the standard path for most projects, which will follow C403.1.1 and sections C403.2 through 403.17. This includes all of your prescriptive requirements like the equipment efficiencies, the ventilation, the economizers, the controls, and so on. As you notice, option number 2, it specifically now says data centers. Before, if you see the exception at the bottom, it says data centers are exempt from these requirements. Now there's not an exemption. There is a different option that you take when it's data centers. So data centers no longer have exceptions or exemptions, but are now have their own dedicated path. They must comply with section C403.1.1, C403.1.2, and 403.6 through 403.17. But note the exception below, as we just said a second ago, they are exempt. That's what it was before in the 21. That deals with controls and economizers. This reflects their unique operation profiles and energy use patterns. I know I've had a lot of people reach out to me specifically about we're not on the 24, the 21, or the 18 doesn't address data centers. We got a lot of data centers coming online in our area. Help us through this. So the new one we've got here is option 3, section C409. This was added to provide what's called a total system performance ratio. I kind of fastly ran through that when we did our presentation with SECO. So that's also known as the TSPR compliance option. It allows for compliance to be demonstrated through a whole system performance metrics rather than a prescriptive component by component check. This is a major addition to the 24, and you will see probably more jurisdictions adopting the 24 for that to allow them to having project developers, designers, and builders to be able to get through that a little easier. So as plan reviewers or inspectors, the takeaway here is to identify which path the project team is claiming. The traditional prescriptive route, the data center route, the TSPR performance route. Now that determines what's going to happen next and what pathway that they're following for compliance. So we'll dig more a little bit in the data center side of it. So data centers are some of the most energy intensive buildings we deal with. Their HVAC, their electrical loads are unique. They're continuous and they operate very differently than a standard commercial building. Hence why people are now saying, how do we handle this? For that reason, the IECC does not try to reinvent requirements. Instead, it points directly to ASHRAE 90.4, which is specifically written for data center performance options. So that's one thing that you may look at that if your city is not adopted or allowing 90.4, you're going to look at that more closely. So the core requirement is it must comply with section 6 and 8 of ASHRAE 90.1. The key takeaway is if you're reviewing or designing a data center, compliance comes straight from ASHRAE 90.1, specifically, as we just said, sections 6 and 8, which address mechanical, electrical efficiency, and performance. What's changed with this too, though, is they add clearer language, they updated the definitions, they remove replacement terms. The 24 improves clarity for this section. Older language around design and annualized values for mechanical load, also known as MLC, caused confusion. So this now cleans that up. It's easier for designers, reviewers to understand exactly what the values are when they're submitting that. and then use the uses are, it's an unaltered 90.4 for compliance for data centers. So plan review tip. So when the project identifies itself as a data center, the plan reviewer must shift from IECC mechanical prescriptive requirements to an ASHRAE 90.4 checklist review. So the IECC's usual mechanical sections, built including economizers, controls, ventilations, requirements do not apply. So I will, with the survey email, I just kind of put together, I think it's a 1.5 page data center checklist for plan reviewers that I'll also send out with the survey email. DDC's direct digital controls. So this is the backbone of modern HVAC system controls. Before we talk about advanced controls and default requirements in the 24, we must understand what the DDC system actually does and why it matters. So it basically works with sensors read actual field conditions. So everything starts with real world measurements. Sensors capture temperature, humidity, airflow, pressure, whatever the system needs to make decisions. Then that signal is actually converted into analog or binary into a digital form. These sensor signals are usually analog. They're 0 to 10 volt signals, or binary like off and on contacts. The DDC controller converts those reading into digital, so now they can analyze it. Then the controller uses program logic to decide what the HVAC system should do. This is where the intelligence starts to happen. The microprocessors compares sensor input, set points, run times, and the program logic sequence. So such as, should we be heating or cooling, or should we be adjusting ventilation? So should we also change damper position? Then the controller decides. The output signal controls the equipment. Then the controller converts digital commands back to analog or binary. These operate the physical equipment, the VAV dampers, the valves, the fan speeds, the economizers, the compressors, and so on. The system can monitor trends, alarms. It can optimize performance. So this is the big benefit of the DDCs. It allows continuous monitoring, trend logs, performance analysis, alarms, optimization. So in the 2024, these capabilities tie directly into the newer requirements for DVC or DCVs, which in also the occupied standby, ventilation resets, and also essentially the fault detection and diagnostics. So in the 21, we had that fault detection and diagnostics. And then now this is enhancing the DDC control so that these things are real-time and active, so they're actually pushed an email to someone when something goes wrong, has recommendations, or it can adjust and fix itself in real time. So to that C403.2.3, fault detection and diagnostics. So the 24 specifically expands this section now in the requirements. So designated in the blue section here, it says any building 100,000 square feet or larger that has one or more HVAC system controls that are controlled by DDC must now include an FDD system. It's all acronyms. So it's fault detection and diagnostics. This is a major expansion compared to past versions, which basically only applied the FDD to certain types like packaged rooftops. So for a refresher, DDCs are the type of the controllers we're controlling and monitoring analog and binary data. We just talked about that. It's going to actually look at temperature or contact closures, convert that into signals that can now be monitored in real time. The intent of the requirement, of course, is large buildings have higher energy losses when HVAC issues go unnoticed. That's where the code's starting to tighten up. Not looking at just efficiencies of the equipment, is let's figure out faults and errors and equipment that is falling apart, basically, or having something that's breaking down. Let's realize that early on before it goes too far. What the FDD system must do is use permanently installed sensors to track HVAC system performance. It must sample performance every 15 minutes, continuously every 15 minutes of the automated data collection, automatically identify and report faults when performance drops, notify authorized personnel when an issue is detected, provide prioritized recommendations for repairing the identified faults, and then transmit these recommendations remotely, not just locally. So emailing someone or having another system off site somewhere that's actually popping a code or a light or a gauge or something inside of a report is telling them that it needs to be fixed or adjusted or just analyzed. Plan reviewers basically verify building size. If it's greater than 100,000 square feet, then this is going to comply or need to comply to that. Confirm the project is using DDC controllers. If yes, then FDD is now required. Look for FDD functions in the sequence of operations, in the submittals and the control narratives and how they're going to list all that. Make sure the submittals include sensor lists, training or trending intervals, alarm logic, notification pathways, etc. And then field inspection tips, check for those sensors that are installed and mapped to the BAS and FDD systems. Confirm trending sequence or frequency is every 15 minutes. So you should and could ask for a demonstration. Have them simulate a fault or review a test log to ensure notifications and recommendations work. Was someone actually notified when there's a fault that was pushed? So in the 2024 IECC mechanical systems section, so nearly all the minimum efficiency tables have been updated, reorganized, or adjusted. I didn't put all of them on here, but tables C403.2.2 or .3.2, 1 through 16 have all been changed in some way. So everything shows up on a blue text if you go to iccsafe.org. So all those actually cover air conditioners, heat pumps, water source units, VRFs, hydronic equipment, all have been revised. Some tables receive new efficiency values, others have just been reorganized, some have updated and to now align with federal minimums or AHRI rating conditions. So what specifically has changed is while specifying values varied by equipment, the most important thing to understand is nearly every category saw an update performance metric. So some equipment types now have new rating conditions to better reflect real world performance. Kind of why it went from a SEER to a SEER 2 is its real world performance, not lab tested performance. Several tables were reconstructed to match current AHRI or DOE test procedures. A few tables add new subcategories that didn't exist in previous editions. So for plan reviewers, when the equipment schedule comes in, you should identify the table that applies to the listed equipment. Verify the rating condition. Is it EER? Is it COP? Is it IPLV? Is it IEER? Is it etc.? Make sure those matched in the required table, and then ensure the unit's listed efficiency meets the minimums. And then watch for mislabeled or outdated AHRI references, common during code transitions. So if you're going to move, your city's going to update into a 2024 and you're on the current 15 or 18 or even 21, make sure that those references are matching. These tables form the baseline. So this is your starting point for HVAC efficiency in commercial buildings. So if you're reviewing mechanical plans, you cannot assume a unit passes from the prior code will now pass in the 24. So you got to verify that all over again. Designers must verify every listed HVAC unit against these updated tables. And then boilers. So looking at boiler requirements, it also has changed up a little bit. The section now includes 3 main areas. You've got combustion air, shutoff, you've got fan motor controls, and you've got oxygen concentration controls for large boilers. These updates focus on reducing wasted energy and improving combustion efficiency. So item 1, we've got combustion air positive shutoff. This is the first requirement, applies to large boiler system, those that are combining an input of 2.5 million BTUs or more. So if those boilers operate with non-positive vent static pressure, or if the multiple boilers share a stack, the system must include a combustion air positive shutoff. The goal here is to stop warm air from being pulled through the boiler when it's off. So without a shutoff, that stack effect can waste a significant energy, especially in multiple boiler systems. And then item number 2, we have fan controls, anything greater than 10 horsepower. So the boilers with combination or combustion air fan motors 10 horsepower or greater, the code now requires them to be either a variable speed fan motor, or controls that can modulate air down to 50% of design flow based on boiler load. So this is about matching combustion air volume to actual fire rate. Older boilers often run full airflow regardless of the firing level, which wastes a ton of energy and thermal energy as well. So these new controls now ensure the system modulates and operates more efficiently. Staying on boilers, we've got now also that oxygen or concentration controls, the O2 trim. This is a significant update. So the newer installed boilers, 5 million BTUs or larger, and with a steady state full load efficiency under 90%, the boiler must maintain specific stack gas oxygen concentration limits. So 5% O2 for standard commercial boilers, 3% O2 for process boilers. These limits come directly from table 403.3.4.1. So to meet these targets, the boiler must use an O2 trim control, meaning combustion air volume is adjusted in real time based on measured flue gas oxygen. Importantly, the code prohibits old style linkage, no jack shafts or common air to gas to air linkages. So modern independent modulated systems are required. There is an exception though in group R2. The only one exception, it says if 50% or more of the boiler system capacity serves group R2 residential occupancies like apartments, dorms, multifamily, these oxygen limits do not apply. So plan review and inspection tips. When reviewing plans or performing inspections, always start by identifying the boiler size. That input capacity is going to determine what happens next. So 2.5 million BTUs triggers a shutoff requirement. 10 horsepower motors trigger modulated fan requirements, and 5 million BTU triggers oxygen concentration and O2 trim, except for group R2 buildings. So for any zone that controls both heating and cooling, the point of these controls, looking at thermostatic controls, deadband, these controls, basically it's to avoid simultaneously heating and cooling and to ensure the system operates efficiently within a defined temperature range. And to do that, the controls must have separate heating and cooling set points. The first requirement is that the thermostat must allow separate set points for heating and cooling. They cannot share a single combined setting. Both must be individually adjustable by the operator or occupant unless overridden by a BAS. 2, have required temperature range and deadband. So the thermostat must be capable of maintaining a minimum deadband of at least 5 degrees between heating and cooling set points. This prevents rapid switching from cooling to heating, something that basically wastes significant amount of energy, especially during spring and fall and the shoulder seasons. So this is how this is also how the thermostat should be initially configured at installation. We're going to look at commissioning some other time during probably next year's presentation. So have minimum adjustment deadband. So when someone manually adjusts the set point, the system must maintain at least a 1 degree separation between heating and cooling set points. So even if the occupant pushes these settings as close together as possible, the thermostat will not allow them to eliminate a deadband entirely. So there are 2 exceptions here. So 1, we've got a manual changeover system. So if the building uses thermostats that require a manual switch between heating and cooling modes, the deadband requirement does not apply. These systems cannot run both modes at the same time. Number 2, specific occupancy. So for occupancies that require very precise temperature controls, such as labs, hospitals, galleries, clean rooms, or spaces governed by an accreditation standard, the thermostat can be set with a deadband as small as 1 degree at installation. These spaces are allowed tighter control because operation basically outweighs the energy savings of a wider deadband. So when reviewing and plan review, so check the thermostat's type and sequences match and that are capable of a 5 degree deadband. The controls narrative shows separate heating and cooling set points, and the occupancy exceptions are documented if they're claiming that. And then during inspection, verify the thermostat is actually set up with a separate heating and cooling set point. The initial deadband is 5 degrees. And then adjust the deadband isn't less than 1 degrees. And if exceptions are being used, the occupancy type matches what's allowed in the exception. Let's see. Benjamin asked, aren't most of the thermostats have separate heating and cooling modes? That's probably true. Most of them all do. This is just addressing something that's pretty much has happened in the past. They're just writing code in here to assure that that doesn't happen. So, good point. And then Section C403.4.1.3 adds to clarity on how thermostats must allow occupants or system operators to adjust heating and cooling set points. So these rules are closely tied to that deadband requirement we just went through. So we have independent adjustment required. The control, basically the code requires that the heating set point and cooling set point are independently adjusted or adjustable. That means changing one should not automatically change the other. I've seen those in the past happen as you turn it up and the other one changes as well to get closer just using that deadband. It should be independent of each other. No automatic set point shift. So when the user adjusts heating set point or cooling set point, it doesn't modify the opposite set point. So it cannot lock the set points together. We just kind of went through that. But an example basically is what we just said. If someone raises the set point for cooling, basically that it will violate that deadband if they're moving heating at the same time. And then display requirements. There is a display requirement in there. So the code also addresses how set points must be displayed, which is especially important in BAS interfaces and touchscreen thermostats, like what we see kind of here. So the thermostat must be able to display both heating and cooling set points at the same time, or display the set point for the active mode and show which mode is currently active. For example, if it's in cooling, the set point shows 74. This prevents confusion from the occupants and occupiers to ensure system behavior is transparent. This section also ensures that occupants clearly understand that heating and cooling thresholds prevent accidental crossover and supports the required deadband. So it also prevents manufacturers from using simplified thermostats interfaces that hide one's mode set point. Basically something that's happened in the past with other code compliance issues. Plan reviewer tips. When you're reviewing drawings or control sequences, look for independent set point adjustment, separate heating and cooling set points in the BAS or thermostat documentation, clear display logic for both modes or active mode indication, and then the deadband maintenance logic is consistent with Section C403.4.1.2. Field inspections. During field inspection verification, check that the thermostat interface directly. Check that thermostat interface directly. Can the user adjust heating and cooling independently? If so, it meets the compliance. If not, it does not. Are both set points visible, or is it showing an active mode only, showing you the set point? So if you switch it from heating, you'll see that set point. Cooling, you'll see that set point. Whatever's running, that set point is being shown. And then does the thermostat prevent a deadband less than 1 degree? And then does adjusting one set point avoid unwanted automatic adjustments? So that's field verification with that. We've talked about this one on several things in the past, but they continue to keep addressing this slightly and moving it around and adjusting what their requirement is. But one of the biggest sources of wasted energy is large overhead doors or roll-up doors. So basically they have now strengthened the requirement for automated HVAC responses when these things happen. So the code requires now, it says when an operable opening larger than 40 square feet, it used to just say roll-up doors, now it says 40 square feet or larger, is fully open, the HVAC system must automatically take action within 5 minutes. Before it just said must take action. They added the 5 minutes to it. The intention is to prevent heating and cooling from running when large amounts of conditioned air can escape to the outside. So with heating response, the system must disable mechanical heating or reset the heating set point to 55 or less. This ensures the building is not trying to heat when it's basically the door is open. So if it's 62 degrees outside, you don't really need heat, but it's below its set point, then when these doors go up, the heating set point goes to 55. So you're not actively heating. Same for cooling. It must disable cooling or reset the cooling set point to 90. So same thing there. If it's 85 degrees outside or 78 degrees outside, the doors are opened up. You don't really need air conditioning. It's going to set it to 90 so it doesn't accidentally come on. So these controls are meant to prevent simultaneously cooling, mechanically cooling or heating when you've got uncontrolled outside air coming in. This happens a lot with sports bars, like retail spaces, but now we're also looking into their loading docks, things like that. When doors open up, those warehouses, if they're being conditioned, must also be tied in. So there are very important exceptions here, though. There are things that are meant for situations where the requirement is either impractical or unnecessary. And I'm going to pause with that, saying that there's a lot of people that may start using those language or that language to get away from this. Is it impractical or unnecessary? I don't know why they put that in the code, but such as automatic closing building entrances. So in other words, if you have doors that close on their own because they have hydraulics that shut down, the HVAC system doesn't need to react. That's also why they put that 5 minutes in there. Is if doors open and close, then that's less than 5 minutes, so it shouldn't have to interact. If it's an emergency exit with alarms, so these openings are not used routinely, so it won't affect HVAC if they're propped open. Spaces without thermostats or sensors, so if there's no temperature control in the first place, the interlock is irrelevant. Food prep areas, so cooking equipment specifically drives space temperature, making these interlocks ineffective or disruptive. So you got to remember, looking at this, it's got to be specific. It can't just be, well, we don't find it necessary. It's got to be specific. Warehouses with approved design, so often tied to specific ventilation strategies approved by the code official. They may not require these. Vestibules, the first opening of that door, the ones to the outside, not the ones to the inside of the vestibule. So only the exterior door is regulated. The inner vestibule doors are exempt. So if those are left open, it doesn't change anything. But if the ones to the outermost outside is open, then that does change the thermostat. So radiant heating and cooling system, these work differently from forced air and does not respond quickly to open and closed doors. Approved alterations, so if there's any remodels or alterations or change of occupancy, basically it may not be feasible to do this. And then air curtain doors. If you've got air curtains over the doors, which air curtain doors are Section C402.6.6, this requirement does not apply. So plan review tips: look for clear HVAC interlock sequences in the controlled narrative. Identify the operable openings. Are they greater than 40 square feet? If they are on the plans, then you need to find where it's tied into the HVAC system, or it meets one of these exceptions that are listed as impractical or unnecessary, or if the code official has made that call. Confirm the set point reset values are 55 degrees and 90 degrees appear on the programming documents. And then field inspections. Test one of the openings. Simulate the door being open for more than 5 minutes. Does the heating shut off, or does it change the set point? Or does cooling shut off or change the set point? So confirm that response occurs within 5 minutes. Otherwise, it is not compliant. Humidity control is one of the biggest energy use drivers in commercial buildings, especially in Texas. The IECC sets limits on both dehumidification and humidification to prevent overconditioning and wasting energy. So now there is a humidification, dehumidification control. So on the dehumidification limits, the first rule is about how low mechanical cooling is allowed to reduce humidity. So mechanical cooling cannot drive humidity below 55 degree dew point or 60% relative humidity, whichever is lower. This ensures systems aren't running cooling aggressively just to chase extra dry air. This wastes a ton of energy. However, the code does allow lower humidity if cooling is running, especially if temperature controlled and not humidity controlled. Dehumidification exceptions. There are some facilities that are generally require tighter and lower humidity standards, such as museums and hospitals, clean rooms, labs, archive storage. These zones must have at least a 10% relative humidity deadband, so ensures equipment is not consistently or constantly cycling off and on. The second exception allows for spaces that meet strict humidity standards, so within plus or minus 5% relative humidity, so to use more precise controls strategies when required by the code. And then humidification limits. On the humidification side, the code prohibits using fossil fuel or electric humidification to raise relative humidity above 30% in the warmest zones served. That'll be something to have to figure out when you're looking at it from a plan review. This prevents unnecessary humidification during times when indoor humidity can create mold or comfort issues. Again, these exceptions apply to very specific occupancy types. So look at those and make sure you're checking that before calling that out. And then sticking to that, we also now have a control interlock. So this requirement basically ensures humidification and dehumidification equipment cannot run at the same time. Yeah, that probably does happen from time to time. It's not commissioned properly or someone's put the settings incorrect. Systems must have a control interlock, so either mechanical or DDC based. So this prevents one system from adding while the other one's trying to remove it. So simultaneous operation is both wasteful and a sign of poorly configured controls. Back to, you got cities now requiring commissioning. These type of interlocks would be on a commissioning list to verify that they actually meet the requirement. There are exceptions for the interlock though. Zones requiring very precise humidity, we've already talked about that, within plus or minus 5% relative humidity may use this simultaneous operation, but this must be specifically justified by code, accreditation, or approved by the authorized authority having jurisdiction. So code officials can make that call. Why this matters is humidity control is one of the biggest contributors to HVAC use in commercial buildings. This requirement basically helps to prevent overconditioning, reducing waste energy, and to ensure set points and system operations in a coordinated way. I think humidity is going to become more of a priority in design of systems than just working with the temperature itself. In residential eventually, but commercial probably is going to happen first. This is kind of the start of what they're trying to do here, is starting to tackle that humidity issue. Plan review tips. So look for humidity set points and deadband values in the controls narrative. Confirm equipment cannot exceed humidity thresholds. And then verify there's an interlock logic between humidification and dehumidification, unless it meets that exception. Field inspection. Check controls trend log for simultaneous heating and humidification and dehumidification. So if it's been running, show me the logs. Make sure it has not ran at the same time. Verify actual relative humidity limits in the building's automation system. That's the BAS. And then confirm the exceptions, if they're using them, are justified and clearly documented. So relief of access outdoor air. So under the air economizer sections, the C403.5.3.4 covers how buildings must relieve access outdoor air during economizer operations. So economizers bring large quantities of outdoor air for free cooling, but they can create overpressurization of the building, and we want to make sure that doesn't happen by adding adequate relief path. So when an economizer opens, outdoor air increases coming in dramatically. So if the building doesn't have a proper relief strategy, it becomes overpressurized, leading to doors blowing open or difficult to close, infiltration through the building's envelope, which is energy waste, poor comfort, drafts, balance and pressure imbalances, and then reduced system performance. So the code requires a defined relief method to avoid all of those. So option 1, return or relief fan. So the first compliance path is using either one of those, a return fan or dedicated relief fans. These fans remove excess air and maintain proper building pressure. To comply, they must meet the requirements found in Section 403.11.1, which covers fan efficiency and control requirements. Option 2, a barometric or motorized damper relief. So the second option allows either one of those. The key conditions are the relief path must have a very low pressure drop, less than 0.10 inches of water column. Basically, that's again goes back to commissioning and making sure that that's meeting those levels. This ensures the system can relieve pressure without adding unnecessary fan energy. And then the required relief airflow must equal design supply airflow continuous exhaust rates, especially exhaust fans like restrooms for those makeup airs supplied by the economizer. So locating the relief outlet, so the relief outlets must be placed so that the discharge air does not recirculate back into the building, kind of like in residential when you have mechanical ventilation. So this is a common design mistake. So if the relief air gets back into the indoor intake, then the system becomes unstable and wastes energy. Plan reviewer tips. So check whether the design uses the fan relief or damper relief. Verify pressure drop calculations for pressure relief or damper relief. So it's that 0.10 inches of water column. Confirm relief airflow calculations. So supply minus continuous exhaust. Then ensure the mechanical plans show the relief outlet location and make sure it's not close to that inlet. And for field inspection tips, observe economizer operation and verify the relief path opens as intended. And then check that the relief outlet is not located near the opening for the intakes. And then confirm return relief fans operate accordingly with the economizer position. And then the DCV, which we talked about just slightly earlier, talking about the DDC. So now it's expanded. I think this all started coming out on the 21, and now it's expanded in the 24. The requirement significantly adds several new triggers. So many of these are shown in blue. I did not put blue. I apologize for that. We'll just go through them. So single zone system with air side economizers, that's new. So one of the biggest changes is that any single zone system with a required economizer must now include a DCV. So this is new and expands the DCV to many rooftop units in commercial buildings. And I should have said this in the beginning, but this is what the code book is written and how it's published. This is not a final version of either a Texas approved, amended, and adopted code or a jurisdictional approved code. So this will all be up to cities, jurisdictions, and code officials to determine whether these things are required, but this is what the code book states. And then space size thresholds are updated. So the second change basically is revising the 250 square foot threshold in colder climates, such as zones 5A, 6, 7, and 8. And then all other zones stay at 500 square feet. The DCV also applies only to spaces with plus 15 occupants or more per 1,000 square feet, consistent with the IMC. A new system types triggering the DCV, basically it adds 3 new triggers. So air side economizers, so automatically modulating outdoor air dampers. So the design outdoor air is greater than 3,000 CFM. These additions makes the DCV applicable to more air handling units and rooftops. So there are exceptions updated by climate zone. So the exception for systems with energy recovery have new square foot thresholds based on climate zone. These are basically now universally lower and better aligned with energy recovery requirements. This is having more stakeholders in those meetings or be able to align the requirements of something else that added to confusion in the 21. Other clarifications: multi-zone system without direct digital control, the DDC, are exempt. So since the DCV requires a DDC to function. 5, new engineered ventilation exception. A major addition to that is an engineered ventilation system designed by a registered design professional may be exempt if it can prove that contaminant levels would otherwise exceed allowable dilution rates, or outdoor air can be reduced by at least 15% without degrading indoor air quality. And then this gives engineers more flexibility on basically complex ventilation systems. These updates expands the reach of the DCV across more buildings, especially schools, gyms, offices, conference rooms, retail spaces. The intent of this is to reduce the indoor intake while spaces are partially occupied, saving fan and heating and cooling energy. So we already have seen occupant sensors in the buildings for commercial. This is now basically basing it on a certain occupant size. Plan reviewer tips: identify any space that's greater than 250 or 500 square feet with more than or equal to 15 occupants per 1,000 square feet. Then that's when these things will kick in and be triggered. Check whether the system has an economizer modulating outdoor air damper or an outdoor air is greater than 3,000 CFM. And then verify DDC capability for multiple zone systems. Lastly, confirm exception documents for energy recoveries or engineered ventilation have been documented clearly, and they're taking those exceptions. Field inspections: verify that CO2 sensors are installed and located correctly. Confirm the outdoor air damper modulates with occupancy. Trend logs or the BAS data basically should show reduced outdoor air at lower occupancy count. And then check that the DCV sequences do not conflict with minimal ventilation rates. I know that was a long one. Parking garage ventilation controls. They continue to keep updating this as well. So C403.7.2 covers ventilation energy controls specifically for enclosed parking spaces. So these spaces often have large fans that run continuously. The 24 requires better control strategies to reduce energy use when contamination levels are low. So when there's very few cars in there, things of that nature, that's going to actually reduce the fan run. Though, we have a separate system for each garage. So this first requirement is that each garage section must have its own ventilation system and its own control system. Same thing with like HVAC systems. Each one needs to have their own thermostat. This allows ventilation to be controlled independently. So if one has a higher CO or NO2 levels, the other does not ramp up. It's just the one. Importantly, the code does not force you to divide a garage into multiple sections. It just says if the garage is divided, each section must have its own, not that you have to separate it. 2, fan airflow must reduce when contaminations are low. So parking garage ventilations must be able to automatically reduce its fan speed down to a minimum of 0.05 CFM per square foot and no more than 20% of the design airflow. This essentially ensures turn down capability for low use or low contaminant periods. Fan power requirements: at 50% airflow, the fan motor cannot use more than 30% of its design wattage. This requirement drives the use of variable speed drives such as VFDs or ECM motors, which most of them are made with now anyways, or high efficiency fan system. So this protects against inefficient throttle control fan systems that waste a lot of energy. And there is exceptions. There is one exception. It's designed for very small garages. So the ventilation system motor must be a 5 horsepower or less. That's what's going to determine it to be a very small garage. And the garage parking section must have no mechanical cooling or heating. So if both are true, the advanced turn down and power requirements do not apply. So parking garages represent a major opportunity for energy savings. Older garages typically run fans continuously at 100%. The 24 now forces the system to have intelligent controls to reduce airflow and energy use while maintaining safety throughout the contamination sensors and proper logic controls. Plan review tips: confirm whether the structure has multiple garage sections. If they do, they need to have their own system for each one. Verify each system has that dedicated control. Check fan schedules and sequences for turn downs that are less than or equal to 20%. And then validate that the 30% fan watt limit at 50% airflow should be in the probably in the manufacturer's information. And then ensure proper contamination detection for CO and NO2 sensors. Field inspections. Observe the fan's operation during low load conditions. Confirm VFD operation and minimum fan speeds. And then check sensor placement and calibration. And then verify the total motor horsepower is using the exception if being claimed. It's got to be less than 5 horsepower or less. That way it can be exempt. Non-transient dwelling units, so new energy recovery requirements for these units in commercial buildings that function like permanent residents, such as apartments, dorms, assisted livings, or extended stay facilities. The 24 requires that these units use outdoor air energy recovery unless they fall under specific exceptions. This refers to the process of capturing both sensible and latent heat from the exhaust and transferring it into the incoming air. So main requirement is provide an ERV. So the code requires an ERV, an energy recovery ventilation, for all non-transient dwelling units. Again, this is what the book says. This may be different in your local jurisdiction. ERVs reduce heating and cooling costs by transferring energy between the outgoing exhaust air and incoming outdoor air. That's kind of what an ERV will do. Option 1, this option basically requires the ERV systems to have at least 50% enthalpy recovery. I'm not sure if I said that correctly. At cooling design conditions and 60% enthalpy recovery at heating design conditions. These values reflect the system ability to exchange both heat and moisture. So then we've also got sensible recovery plus moisture transfer. There's the second pass for that. It does get more complex. The SRE, is greater than or equal to 65% at 32 degrees. And for humid climates, such as what most of Texas is under, and then you've got the net moisture transfer of greater than or equal to 40% at 95 degrees. So the SRE covers basically heat transfer only, while the NMT reflects ERV's abilities to transfer moisture. There are climate-based exceptions. So climate zones 3C is the ERV is not required. Units under 500 square feet in climate zones 0 through 5, well, basically very small units in these zones, are exempt. Heating conditions, basically these zones are rarely experienced significant heating loads, or when you've got cooling in climate zones 4 through 8, these zones also experience less cooling, so that's in the colder climates. The ERVs significantly reduce the energy penalty associated with bringing indoor or in the outdoor air. This requirement ensures that multifamily residential units inside commercial buildings maintain good ventilation while also reducing heating and cooling loads. So on the plan review tips, we've got confirmed each unit qualifies as a non-transient dwelling unit. Also check the ERV performance meets either the empathy or the SRE and NMT path. We can go into more of that if you want, or have call me with that. We can go through that. So check climate zone to determine which exceptions may apply. And then field inspection tips, verify the ERV installation matches submitted ratings. And then check airflow balancing, so supply and exhaust ratios, as well as confirm condensate drainage for the ERV. That's very important, especially in humid climates. And then inspect the controls for frost prevention and bypass functions. Probably not so much in Texas, but check those as well. Commercial kitchens, those have changed up just a little bit with the exhausts that are in that. There was a fan efficacy for those, but now they're starting to address even different sizes of the equipment. So one of the largest energy uses in restaurants, food services, institutional kitchens, the 24 now has a more stricter control for makeup air, airflow reduction, and when DCKV is required. So that's the digital control for kitchen ventilation is required. So replacement air requirements. So the code limits how much replacement air can be introduced directly into the hood's cavity. It cannot exceed 10% of the hood's exhaust rate to ensure the hood is not flooded or remains and it remains effective. So conditioned supply air must be also limited, so it cannot exceed the larger of what is needed to meet heating and cooling loads, or the difference between hood exhaust and available transfer air from adjacent spaces. This basically is preventing oversupplying conditioned air just to feed the vent hood that's venting to the outside. And then direct controlled kitchen vent requirement for hood type 1 says one of the biggest items here is the mandatory use of those controls when the total type 1 hood exhaust exceeds 5,000 CFM. So that DC-kV system must be able to reduce exhaust and makeup air by at least 50% during idle periods. So moderate airflow based on actual cooking activity. A lot of that will probably be in the manufacturer's data. Always maintain full smoke capture and containment. Use the hoods that are factory built and listed by a recognized tested lab. There's some that are probably out there that don't have those tested lab certificates. This basically prevents constant 100% airflow operation, which basically wastes a lot of energy. So just running them consistently. Multiple hood sections. There are multiple appliances with different duty ratings share a single hood, all under one. The design must meet the highest duty rating. So this ensures capture performance to maintain the most demanding appliance that's there. There are exceptions. They're called low flow UL rated 710 hoods. These hoods basically have a maximum airflow of basically less than or equal to 250 CFM per linear foot, and having a total exhaust of less than 5,000 are exempt. These are specialty lower flow hoods that inherently reduce energy use. Number 2 exception is an ERV. So ERVs are allowed when the SRE is greater than or equal to 40%, and then its airflow is greater than or equal to 50% of its total exhaust. This allows kitchens to recover some of the heat from the exhaust air under specific certain mechanical code conditions. So kitchens often run high exhaust continuously, so that DC-kV a requirement now allows for dynamic reduction of airflow, dramatically cutting heating, cooling, and fan use, especially in restaurants and cafeterias. So plan review tip here, check total flow hood airflow. If it meets that and it's triggered that DC-kV at 5,000 CFM or greater. Confirm that DC-kV control in sequence of operation. Confirm the hood's listing and model certification. Verify replacement air calculations for compliance, and then look for ERV only if they're allowed under the IMC. And then field inspections, verify the DC-kV sensors, the temperature of the if it's got an optical or IR, make sure they're installed correctly. Confirm airflow modulation, so trend logs or live BAS data. And then test the idle reduction function is basically reducing it to that 50% reduction. And then inspect the hood's label. Is it UL 710 listed? And lastly, verify airflow balancing matches the hood's duty rating. So is it meeting that larger of the two equipments? And then we've got 403.7.8 to 9, occupied standby ventilation controls. So that's now been expanded, which is one of the key energy saving control strategies of the 2024 IECC. These rules apply to many commercial spaces, commonly commercial spaces, and are defining, basically it defines exactly how the HVAC system should behave when rooms are unoccupied. Controls are just being expanded from what it was done in the 21. So the 403.7.8, it says where occupied standby is required. The code lists specific spaces that must have standby controls. These are areas with intermittent uses such as classrooms, meeting rooms, break rooms, offices, corridors. The intent basically is to reduce energy use when occupant sensors indicate the space is empty. So it's not just lights anymore, it's also that HVAC systems. Importantly, if a system is part of a multi-zone system without automatic dampers, it is exempt because the airflow cannot be individually controlled for just that one unit. The 403.7.8.1, what happens during standby mode? So when the space transitions to standby mode, usually based on time of day or occupant sensors, the HVAC system must adjust within 5 minutes. That's a common theme in the 24 as they've added these 5-minute allowances. The code requires 3 actions. Heating setback of at least 1 degree, cooling setback to at least 1 degree. This widens the deadband to reduce cycling. And then shut off air supply whenever the temperature is between the heating and cooling set points. So this will now prevent the unnecessary ventilation in unoccupied spaces. This is all about reducing, basically, conditioning and air movement when the zone does not need it. So shutting down things and saving energy in places that there are no occupants. And then multi-zone system requirements. If it's a multi-zone system, standby mode must also include a reduction in outdoor air. So now we're tying more systems into this. So the system must reset the effective minimum outdoor air set point to account for zones that are unoccupied. Key requirement: standby zones must have 0 outdoor air supplied to them when they're in standby mode. And the air handler unit must allow an approved outdoor air reset logic that reduces ventilation load without compromising indoor air quality in the occupied zones. And then a dwelling unit ventilation system. The final section basically clarifies ventilation for dwelling units within the commercial building. A heating and cooling fan system, like blower in a split system, cannot be used as the outdoor air unless its fan efficacy meets the 1.2 CFM per watt under no load conditions. So this prevents inefficient blowers from being used and to provide continuous ventilation. Kind of the same thing that residential has, is that fan efficacy table that air handlers must meet the same requirement, the 1.2 CFM per watts. These standby controls significantly reduce energy waste by cutting airflow, reducing mechanical heating and cooling, and lowering outdoor air demand when rooms are unoccupied. So all without compromising comfort when the space becomes occupied again. Plan review tips. Confirm occupant sensors, the types, and the control sequences. Verify airflow shutoff capability, so zone dampers are required. Check outdoor air reset logic for multi-zones. And then verify dwelling unit ventilation systems meet fan efficacy requirements. Field inspection tips. We got test the sensors activation that verify that 5-minute response. Confirm airflow shuts off during standby. And then check BAS trend logs for outdoor air reset. And then also you can measure fan efficacy if using HVAC fans for ventilation. You'll have to do that what's the CFM and then divide it by the watts and see if you get that 1.2 CFM per watt. Otherwise, it is not compliant. They are now addressing that low capacity ventilation fans. Before it was just showing for those large kitchen vent hoods and things. Now it's lower ones. So for small capacity mechanical ventilation fan, those motors that have under 1/12 horsepower, which also can include things like bathroom exhaust, inline fans, utility room fans, low capacity ERVs or HRVs. The 24 now requires standardized testing and minimum fan efficacy levels to ensure these smaller fans perform efficiently and consistently. Same thing we have in the residential side. Applicability, basically this applies to any mechanical ventilation fan under 1/12 of a horsepower. That covers most residential style fans. So if you have the Brones, the Aprilaires, the small inline fans, or you have these bathroom fans, storage room fans, small offices, utility rooms, or any other kind of inline ventilation system is what this applies to. Testing and documentation requirements. The airflow must be tested using an approved test procedures referenced in the table 403.8.5. The results must be listed on the product and or derived from a manufacturer listed airflow and input wattage. So you can look at that part of it and see, and this ensures the inspectors and designers can verify performance without guesswork. Fan efficacy requirements. That efficacy airflow delivered per watt of input power is central to this section, just like it is in residential. So the code requires these fans to meet minimum fan efficacy values, preventing the use of basically outdated, inefficient large fans to pull small airflows. Static pressure test conditions to ensure real-world performance. Code sets minimum static pressures to be used for testing as zero point 0.2 inches of water column for fully ducted ERVs or HRVs, balance system, or inline fans, and then a 0.1 inch of water column for ducted bath fans, utility fans, and ducted range hoods. These pressures reflect typical installed condition and ensures the fans are not underrated, are not rated under unrealistic low restrictions, such as poorly installed ducts can dramatically change that pressure in that inches of water column. So to test it and verify and validate CFM, this is the test pressure that you're looking for. There are exceptions. There's 5. One is part of the listed HVAC appliance. So if the inline fan or whatever you're working on is part of the HVAC system, like a furnace, then it doesn't have to be tested separately. If it's an appliance type exhaust fan, so dryer exhaust fans, range hoods, booster fans are exempt because they operate intermittently and have their own regulatory standards. Radon mitigation fans, these fans are purpose built and regulated separately. Fans outside the reference test standards, so if the fan type is not covered under their test procedures, it's exempt. Ceiling fans, of course, is also exempt. They have a specific federal standard they must follow. So small fans may not be a major energy use individually, but when you have multiples being used in multiple units and then you multiply that times what it is in the commercial building, that adds up. So ensuring that they meet minimum airflow and efficacy requirements improves both energy efficiency and indoor air quality. So plan review tip, verify product submittals show airflow and wattage, or you'll have to look up in the manufacturer's paperwork. Confirm fan types fall under the required test method. Check static pressure readings or ratings used for testing. So that would be by a third-party commissioning. Identify whether an exception is being used in that, and they're taking that one of 5 exceptions. Field inspection, verify equipment label matches submitted performance. So what they did in plan review is actually what they installed. Check ducted or ducting is installed, so static pressure approximates tested conditions. In other words, verify that the duct is not compromised, crushed, kinked, sharp bends, things that are going to reduce or raise that static pressure and lower airflow. And then ensure no prohibited fans are used in ventilation applications. There are now also intermittent exhaust fan controls for bathrooms and toilet rooms. So when a bathroom or toilet room is designed to operate intermittently, which most of them are, but in commercial, most of them run continuously. But it basically means it cycles off and on rather than run continuously. The 24 requires certain control strategies to ensure exhaust is used efficiently and does not run longer than necessary. So manual on requirement. All intermittent bathroom and toilet exhaust systems must provide at least a manual on control. This ensures the system only runs when needed and avoids unnecessary energy use from continuous operations. So 1, a timer control is less than or equal to 30 minutes. So a timer can be used. It must be limited to no more than 30 minutes. This prevents the fan from running excessively. Occupant sensor shutoff is less than or equal to 30 minutes. So once the person leaves, it will shut off. Humidity control, it's going to be either between 50 to 80% relative humidity if you have a humidity sensor. So minimum set point must not be greater than 50%. Or less than 50%. The max cannot be greater than 80%. This prevents the user from disabling the fan by choosing an unreasonable high humidity setting. And then if you have contaminant-based controls, these controls activate the fan in response to air quality triggers such as VOCs, parts per million, particles, CO2. The code now allows these systems to have alternate ways of basically ensuring proper ventilation when the space is occupied. There is exceptions, so are occupancy integrated systems. There's one important exception. So if the bath or toilet exhaust is part of the outdoor air ventilation system or for multifamily or residential group type R2, R3, and R4 buildings, then only a manual on control is required. So that's if that bath or toilet exhaust is part of the outdoor ventilation strategy system for multifamily or in group 2, 3, and 4, it only needs a manual control. However, the code is clear that an offset point is not allowed to meet minimum requirements. So the system must still meet the ventilation design intent. So that means that still has to be tested. Bathrooms generate moisture, odors, pollutants. These controls basically balance that indoor air quality with energy efficiency by ensuring fans only run when needed and not indefinitely. Plan review tips for this one is verify control type. Is it timer? Is it occupant sensor? Is it humidity sensor? Is it contamination sensors? Confirm the limits and their settings. Is it equal to or less than 30 minutes for everything except humidity? And then the humidity is anything is 50 to 80% equal to or less than that. Well, it's going to be between that range. And then check whether there are occupancy exceptions are applied for. If they are, then verify that they are meeting those exceptions. And then field inspections, test for a manual on function. And then check the sensor shutoff times. And then verify humidity sensors are within code allowed limits. And then confirm the system isn't using an offset point to bypass requirements. This basically is for large warehouse fans. So we've got the 2024 now sets efficiencies and labeling requirements for large diameter ceiling fans that are most commonly used in warehouses, gymnasiums, large volume spaces. This goal ensures basically the fan delivers high airflow with minimum energy consumption. So testing and label requirements. All large diameter fans must be tested and labeled per using an AMCA 230, which is an industrial standard method of testing fan performance. The fans must also meet the efficacy thresholds listed in table C403.9. The minimum efficiency requirements. The code requires 2 performance checks. At max speed, the fan must achieve a CFEI of at least 1. And then at 40% of max speed, or nearest available speed, the fan must achieve at least a 1.31. This ensures the fan is both efficient at full speed and partial speed, which reflects real-world operations. And then we've got, of course, U.S. and non-U.S. applications. There is in the table, there are 2 rows, one for outside the U.S., one for inside the U.S. The different exists basically because the Department of Energy regulates ceiling fans under a different requirement. And then understanding that CFEI basically is for ceiling fan index, it's performance metrics that compares the actual fan's power use to a reference fan using the standardized AMCA 280 calculations. Practical takeaways for plan reviewers: verify that submittals include test data using correct test procedures. Check that the CFEI values at both max speed and 40% or relatively around the closest speed that you can get, if maybe it's 50%. Confirm labeling matches the AMCA 230 requirements. And then review whether the project location uses U.S. or non-U.S. That's probably going to be not applicable for that. And then field inspection considerations. Physical fans should be labeled and as tested. And then installing fans or installed fans must match the approved model number, so verifying what was on plan review actually matches what was installed. And then some jurisdictions may also require spot check speed control settings as well. And I believe, I did not put that on there, but I believe the fan diameter is basically anything 84 inches of a blade span or greater is considered a large fan. So large commercial boiler systems, especially for those who are over 1 million BTUs per hour, these systems are commonly found in large schools, offices, hospitals, government buildings. The code now introduces requirements to increase boiler efficiency and improve hot water distribution design. So applicability and intent. These requirements apply when total boiler plant capacity falls between 1 to 10 million BTUs per hour. This captures mid-size and large boiler plants but excludes small systems commonly found in small commercial buildings. The primary goal for this is to push boiler plants towards higher efficiency and better return water management, which significantly reduces energy consumption and improves condensing performance. So there's exceptions to this. The breakdown of that is there are 4. If at least 25% of the annual space heating is met with renewables, that's going to be starting to show it's exempt. And then any individuals that fall under the 300,000 BTUs per hour is ignored when calculating plant capacity. The boiler efficiency, all gas hot water boilers must have a minimum of 90% thermal efficiency based on the test standards in the table. For systems with multiple boilers, the code allows an input weighted average. So you can add those together and divide by and get an average for that part of it. If a boiler is only combustion efficiency rated, then the number is used for that calculation. And then hot water distribution design. This section ensures that the return water temperatures are low enough to allow condensing boilers to actually condense and achieve high efficiency. So 2 main requirements there. Heat exchangers must be sized so that the design load water coming back to the boiler is 120 degrees or less. Under all operation conditions, either the return water entering the boiler stays 120 or less, or flow through a bypass piping like a 3-way valve must be less than or equal to 20% of the design, preventing hot water returning from the bypass system and degrading the performance. So these requirements help ensure condensing boilers operate efficiently and full performance and is maintained during part load. So plan review tips for that. Confirm boiler capacity falls within that 1 to 10 million BTUs per hour range. Verify thermal efficiency is greater than or equal to 90% in submittals. Check multi-boiler efficiency calculations for correct area or average weighting. And then weigh coil and heat exchanger schedules. Review coil and heat exchanger schedules for that 120 return water temperature. And then ensure bypass flow limits are clear in engineer's design narrative. Lastly, you got field inspection tests or tips that are here. Confirm installed boilers matched the approved model numbers that were in plan review. Verify return temp sensors are installed and calibrated. And then observe piping to ensure no unauthorized bypassed arrangements. Not that the energy code is getting into more of the water stuff, but it does talk heavily about minimum pipe insulation thickness. So as you see here in the table, 403.13.3 parentheses 1 provides requirement for minimum pipe insulation thickness for mechanical systems in commercial buildings. It covers everything from the chill water lines to the high temperature steam. It basically dictates how much insulation is necessary to limit heat loss or gain and improve system efficiency. How this table works is the table is organized, basically it organizes its requirements into 3 variables. So first one, fluid operating temperature. It's broken into ranges from 40 degrees up to 350 degrees. So insulation conductive. So basically it's provided as a range of typical values for commercial insulation materials. Pipe size is divided into 4 size categories. You got 1 inch, 1 to 1.5, 1.5 to 4, and anything greater than 8. High temperatures and larger pipe diameters naturally require more insulation. The high temp range for piping carrying fluids above 350, the insulation requirement is typically 5 inches regardless of pipe size. So temperatures between 250 to 350 require 3 inch to 4 inch or greater, depending on the pipe diameter. Anything over 350, it doesn't matter what size the pipe is. Mid-range temperatures. So for water temperature between 105 and 200, the required thickness of the insulation basically is 1 to 2.5 inches. Most hydronic heating and surface water heating systems fall into this category. Low temperatures such as chilled water or glycol systems below 40, insulation is required primarily to prevent condensation and maintain energy performance. Its requirement ranges from 1/2 inch to 1 inch depending on pipe size. And then R value versus the pipe size in inches. The table basically has 2 compliant pathways. So insulation thicknesses or the R value. So this allows flexibility in selecting the type of material that you're using. You're just looking for it to meet one or the other. So adjustment notes, there are 3 key adjustments here. Small pipes and interior partitions can reduce insulation by 1 inch, but never below 1 inch. If the insulation used is a conductivity outside of the range, if it has a conductivity outside the range, the code provides a formula to calculate the equivalency thickness. So direct buried system basically may reduce insulation by 1.5 inch, but again, no pipe may have less than 1 inch of insulation total. These adjustments again allow for flexibility while maintaining minimum performance. Plan review tip, verify insulation thickness or R value matches the table for correct fluid temperatures. Confirm insulation conductivity matches tested values or adjust using code formula. Check whether an adjustment notes apply, like such as a small pipe or buried piping, actually trying to do the reduction of the thickness of insulation, but never less than 1 inch. And then field inspection, measure insulation on site, especially large diameter hot water piping. Ensure insulation is continuous, properly sealed, and installed without compression. And then watch for uninsulated fittings such as elbows, valves, flanges. Those must be insulated to the equivalent performance or R value or thickness required depending on temperature and pipe size. So the second table of that, though, is also providing minimum R values for this. Key concept here is R value represents basically thermal resistance. So higher R values reduce heat loss or heat gain in the pipe, which improves its efficiency and protects against condensation, temperature drops, or equipment oversizing. So these R values are dependent on fluid type that is inside of the building, inside of the pipe itself. Temperature bands. So fluid temperature is primary driver for insulation performance, as we talked about earlier, but here is their specific requirements. Anything above 350, you're looking at R32 to R36. And then as you can see down the chart, all the way down to 105 to 140 is R5 to R8. Those chill water pipes, 40 to 60 is now looking at R2 and R7, mostly for all those chill water pipes. Anything below 40 has a slightly higher R value due to the condensation control that is needed. And then the pipe size effects, so the table breaks it into those sections. Smaller pipes require higher R value because they lose more heat more rapidly relative to the surface area. So plan review tips, verify fluid temperature classification match the system's operation. So confirm that what it says on the equipment actually is what they're listing on the plans for the pipe. Confirm the R value is shown in the schedules match the table requirements. Check whether the designer used the tables either inches or R value. And then review the insulation submittals for conductivity. So it's basically the K value. That usually comes from whatever manufacturer made the insulation product. You'll be able to find that in those product data. And field inspection tips, check the insulation labeling or manufacturing data for the R value. Should be listed on it. If it is not, you may have to look on the manufacturer's website. And then ensure conductivity or continual insulation for fittings, valves, and unions. All those must still meet that same R value and or inches of insulation requirement. And then look for any compression, any gaps, any missing vapor barriers, usually silver, bright silver, on chilled water lines to make sure those things do not condensate or have a potential of condensating. And then C403.15, now we've got dehumidification in spaces for plant growth and maintenance. There was a section in the 21 that just continues to get expanded and clarified, in my opinion. But these spaces have very high latent loads due to plants, irrigations, soil moisture that must be maintained. Because dehumidification energy can be extremely high in these spaces, the code requires equipment that is either highly efficient and or recovers heat that would otherwise be wasted. So there's several options. First one is listed dehumidifiers. The first compliance path is to use these packaged dehumidifiers that are tested and rated to a DOE standard 10. These standardization tests procedures designed basically to ensure predictability, performance, and verified efficiency. And then number two, integrated HVAC with heat recoveries. So another option is to design the integrated system to also have that, which will include a heat recovery system capable of providing at least 75% of the annual reheating energy required for dehumidification. This approach captures wasted heat. That's what we just said a second ago, and the primary reason why they're there is you're capturing wasted heat. Option number three, chilled water system with heat recovery. Likewise, a chilled water system may be used provided they incorporate on-site heat recovery that also fulfills 75% or more of the annual dehumidification reheat needs. Both integrated HVAC system and chilled water systems achieve the same goal, reducing energy consumptions by recycling internal wasted heat. Option four, desiccant dehumidification. A solid or liquid desiccant system may be used if the space design requires a dew point no higher than 50%. These systems are used for very low humidity applications and are sometimes necessary for specific plants, drying operations, or for disease control. The intent of this section basically is ensuring that grow facilities, which is kind of the key word they'll be using, known for using highly energy intensive equipment, either is using high efficiency equipment and or the systems capable of recovering energy internally. So this helps reduce operating costs, reduce electrical demand, and support sustainability and rapid growth. Plan reviewer, Plan review, confirm whether the space qualifies for an indoor grow or greenhouse area. Verify that the four compliance pathways in the design are used. Check for DOE 10 if its certification is being using those packaged dehumidifiers. For heat recovery systems, require the annual energy calculation showing greater than or equal to 75% reheat contribution. And then field inspection tips. Verify the installed equipment matches the approved submittals. Confirm that the heat recovery components are installed and connected. Service water pressure booster systems. We're running a little bit on off time here, so I'll just kind of speed through this one. Service water pressure systems. Basically, the system increases domestic water pressure in large buildings such as hotels, high-rise residentials, hospitals, and office towers. These systems can significantly waste a lot of energy if not properly controlled. So we've got pressure sensor controls. That's your first requirement. You've got no pressure reducing devices after booster pumps. Then you've got no pump operation when flow. Those booster pumps must not run when the service water is not running or not flowing. This requires protection against unnecessary energy use for overheating and pump wear, wastewater. The system should include a no-flow detection. And then the intent of this one basically is the purpose of that is to prevent, again, energy waste, ensuring properly sized pumps, improve longevity, and pressure booster systems. Plan reviewer tip, confirm control sequence shows pressure-based VFD control or pump cycling. Verify sensor placement or logic simulation strategy. Look for any prohibited PRVs installed downstream from the booster pump. And then review pump schedules for standby and duty configurations. Field inspection, confirm sensors are installed and is shown in the submittals. Test the system to confirm pumps reduce speed or shut off at low flow or no flow. Ensure no unauthorized pressure reducing valves are installed, and then confirm VFDs are operational and tied to building controls. One that we did see added to the 24 is what they call now a clean water pump. So C403.7 sets energy performance requirements for clean water pumps to be used in the commercial buildings. These requirements ensure that pumps operating efficiently at their best efficiency point, BEP, follow updated federal and DOE pump efficiency standards. Only pumps with a pump energy index, PEI, not greater than 1 are allowed, meaning the pump must be at least as efficient as federal baseline. Key performance on the requirement is the system applies only to pumps that are from 1 to 200 horsepower, which covers the majority of commercial hydronic circulation pumps. Each pump must deliver at least 25 gallons per minute, at least 259 feet of head, over a temperature range of 14 degrees to 248 degrees. These performance criteria ensure the pump is capable of real-world operation conditions and efficiency verification. Pump types that are covered in this is the code narrowly defines the pump types covered in the sections. Applicable pumps include in-suction closed coupled, in-suction frame mounted, inline pumps, radially split vertical pumps, submersible turbine pumps. This aligns with DOE's test procedures for clean water efficiency. Motor capability or compatibility, the pump must be paired with a motor that runs at the same rotational speed. This can be a standard 2-pole or 4-pole induction motor or specific non-induction motors that operate with a range of basically 2,800 to 4,300 RPM or 1,400 to 2,100 RPM. This ensures the pump is tested and operated under a standardized condition of speed. The code lists several pump types that are not required to comply with this PEI. Basically, it's fire pumps, self-priming pumps, prime-assisted pumps, magnetic-driven pumps, or nuclear pumps. So plan review tips here. Confirm the pump type is within those allowed categories. Verify the PEI is less than or equal to 1 from the DOE manufactured certification. Check pump performance so the gallons per minute, the head, and the temperature range matches code criteria. Confirm the motor type and rotational speed fall within the allowed ranges. And then identify whether the pump falls under any exemption. If so, it needs to be clarified accurately in the documentation. Field inspection tip. Ensure the installed pump basically matches the approved, it's been approved through the submittal. Verify motor nameplate speed matches the pump speed, and then confirm the pump is exact motor listed with compliant PEI values. All right, I know that was a lot of information. I know you guys wanted me to go deeper into this. I hope this is not too much information for y'all. It's not overwhelming for that. Please leave that in the survey. If it is, I can adjust accordingly as we go forward with the 2024 IECC requirements. But thanks to everyone for joining me today. This was only the new stuff that actually is in the 24, or it has been changed dramatically from the 21 to the 24. It is not everything that's included in the code book itself. So as we continue to support local officials, contractors, energy professionals across the region, please, we invite you guys to stay connected with us. Follow us on LinkedIn or X. Visit our website at eepartnership.org for resources, tools, and training events. We're also on Blue Sky as well at eepartnership.bluesky.social. Also, I've included Kathy's email address here if you guys have any question, and or if you are having multiple people in one room with one sign-on, please email her and verify and validate who's in the room before just assuming that everyone will get it. So we look forward to working with you guys in the future and supporting our team and the industries that are involved. This is my contact information here. Please feel free to share this with anybody that I may be able to help or assist. We will do our best to be able to get them done. So I know that was a lot to take in. Please, please, please let me know in the survey if this is the kind of information that you want to hear and see. If not, I can adjust and have more of an overview. But I wanted to break down each section a little more intensely. That way we can get some requirements and enforcements out there in the field. So thanks again for everybody. I'll stay on for a little bit if you have any final questions. I appreciate everyone being here.